let's continue. The next topic then are independent random variables. So keep in mind again that what we are doing here is all the time to formulate a model, and currently we are formulating probabilistic models, and also probabilistic models, so joint distributions of random variables, are usually used as models of some real-world phenomena, and then they are used to basically model dependencies between entities in the presence of noise. And they can also be used to model the kind of unitary concept of two things not affecting one another. Yeah. And the mathematical model for these two things not affecting each other is the notion of independent random variables. So the idea is, for example, to have to model the outcome of a throw of two dice, where whatever happens to the one die doesn't affect the other die. Yeah. So this kind of probabilistic model is formulated in mathematical terms by, if we have two random variables, x and y, by setting their joint distribution to the product of the individual marginal distributions. And of course, one can ask why. It's actually not that easy to answer that. I think what I can do is show you by example that this works, and then maybe also provide a little bit of an argument. But what's most important, what you take from that is that a joint distribution models the case of two independent things if the joint distribution of x and y taking on specific values is the same as the product of the of x and y taking on these values. So let's look at an example to make that clear. The way that this kind of course, we could now write down a joint distribution, so we could write down something here, and then check whether this actually models a independent distribution over the two random variables. But we can also make our life easier by constructing the joint distribution by actually this product property. And of course, this is also how, if this is used to model two independent things in the world, how this is done. So let's make this more concrete. Let's assume that P equals 1 is 1 over 4. Px, oh, now I'm doing it the other way around, sorry. To keep that, let's call this y. Py equals 2 is 2 over 4, and py equals 3 is again 1 over 4. And then let's say that px equals 1 is 1 over 3, and px equals 2 equals 2 over 3. I should put that down. 2 over 3. So we have a probability distribution over one random variable, which models one thing in the world. And this takes on values 1, 2, and 3, and the probabilities are 1 over 4, 2 over 4, and 1 over 4. So that's a probability distribution because it sums to 1. And then we have another thing in the world that we're trying to model, which takes on values 1 and 2. And has this probability distribution. Now the product rule here, or the product thing, sorry, the product rule, people mean something else by that, means that if we want to construct the joint distribution, we should multiply the marginals. Yeah, so let's do that. So if we now look at the probability x equals 1 and y equals 1, we get 1 over 4 times 1 over 3, so that's 1 over 12. Here we get x equals 1, y equals 2. We get 1 over 3 times 2 over 4, that's 2 over 12. And here we get p x equals 1, y equals 3. We get again 1 over 12. Please correct me if I'm doing something wrong, because that can easily happen. And if we continue filling in here, we are probability for x being 2, y equals 1. Again, we have to multiply this, so we get 2 over 12. Here we get probability x equals 2, y equals 2. I should put a line here, and something right here. So that's 2 by 2, that's 4 over 12. And here we get p x equals 2, y equals 3. And that's 1 over 4, that's 2 over 12. So let's check whether now our joint distribution is actually a probability distribution. So it must sum to 1. So we have 1 plus 2 is 3, 4, 6, 10, 12. So that seems to be okay. And let's have a look at what we actually see for our conditional probabilities, and actually the joint let's look at the joint distribution now. So maybe let's look at the probability over x first. So the marginal was that x equals 1 is 1 over 3, and x equals 2 is 2 over 3. So the probability is twice as large for x being 2 than for x being 1. And now if you look at what happens in the case of y equals 1, you see that's 212 where there's 112, so it's twice as large. Y equals 2, it's 4 over 12 versus 2 over 12, it's twice as large. And the same thing for the last one. If we look at the probability distribution over y, that was in the marginal, it was 1 over 4, 2 over 4, and 1 over 4. And irrespective of what happens with x, somehow the middle value is double the values on each side. Now we could do the reverse and divide it by the marginal, and to get back them we could sum things up, or we could compute conditional. Maybe let's compute a conditional so that we can then see that even stronger. So let's compute p x, the probability distribution over x given y equals 1. So maybe that's now something that you can do. So the first thing that we need to compute is probability of x being 1 given y equals 1. So what is that? So can you tell me how you computed that?
I'm looking at the first row of x and first column of y.
So that's you basically use x1 y equals 1, which is 1 over 12. So that's 1 over 12. But then we have to divide it by py equals 1, right? So if we do that here, we have to multiply 1 over 12 by 4 over 1. So 1 over 12 times 4 over 1, and that's 1 over 3. Did you say that?
No.
No, good. Or not good.
Why is it 1 over 4?
Because the marginal of p, so this is 1 over 4.
Oh, this is okay.
Yeah, it's written there, but you can also compute it by summing again here. So then you have 3 over 12, which is also 1 over 4. But it's the same thing. I mean, we constructed it. So we get 1 over 3 again. And now that the other one, of course, is px equals 2 given y equals 1. And now we could compute it again, but we already know that because it's a probability distribution needs to be 2 over 3. So what you see here is are two things. So first of all, we have seen that if we construct the joint probability distribution in this way, then irrespective of the we haven't quite seen it. Let's do the last thing. Then we have really seen it. So now we have done this, and now let's compute px given y equals 2, because then it should be really clear. So for this, we have to look at this thing here and divide it by 2 over 4. So that's px1 y equals 2 divided by py equals 2. So that's, again, what do we have here? 2 over 12 divided by 2 over 4, or 12 divided by 2 over 4, and that's 2 over 12 times 4 over 2. So then this cancels out, and we have 4 over 12, which is 1 over 3. And again, then we already know that p equals 1, and that's p equals 2, y is 2, must be 2 over 3. So what you see here now very explicitly is that the probability distribution over x given y equals 1 is, for x being 1, 1 over 3, and for x being 2, 2 over 3. And the same thing, exactly the same thing holds for if y equals 2. Then again, for x, there's x being 1, which is a little bit hard to see here. It's 1 over 3, and x being 2, it's 2 over 3. We could do it for the last one, but I'm tired and I will just make more mistakes. What this shows, I mean, you see it again from the joint distribution, but you can explicitly then also recover it. What this means, what this means essentially is that the probability distribution over x given y, so for different values of y, is always equal to the marginal distribution. Yeah, and what this also means is that the probability distribution, very intuitively, over x doesn't change as y changes. Yeah, so y is 1, 2, or 3. Probability distribution over x doesn't change. And we got to that by defining the whole thing as by this factorization property, or by saying, okay, the joint probability of x being some value and y being some value is given by the product of x being some value and y being some value. One can also maybe push that a little bit in the sense that what we have seen now is, and what we also want, is that the conditional distribution over x is not dependent on the value of y. Now, what this means is that px y divided by py equals px. Yeah, so somehow this seems to be the case, right? Because this is just the definition of conditional probability. Now, when does that algebraically hold? Of course, if px, py, so if this joint distribution factorizes, then this actually holds. Yeah, so because in this case, then this holds. So it's the thing is that it's I've shown you now in different ways that a good model for modeling independence, so basically the fact that the probability distribution of one random variable is not affected by the probability by the value, not the probability, by the value of the other random variable. A good model for that is this factorization. Yeah. For everything that you will need in the next couple of weeks and so on, what you should really take from this is that a joint distribution of two independent random variables factorizes in this way. So if you want to model a joint distribution of independent random variables, you should just multiply the individual probabilities. This you can then think about again, and it's helpful. But you don't need to think of all of this whenever you see this. Yeah? Questions about this? No. Everything clear or everything completely confusing now? Smile. Don't know what smile means. In principle, I know what a smile means, but in this case, I don't know what a smile means. Okay, good. So from the whole thing that we've done so far, what you really should get your head around is joint distributions. So let's summarize that again. Joint distributions, something like that you become familiar with this notation, conditional, so that you are happy in principle with this bar notation, marginal, which are of course just distribution over one random variable, but in a joint case are then computed by summing over the other one, and independence by this factorization property. Good. So this is where we are essentially at, and where I hope I have now gave you at least some intuition about these things. Now, what we have dealt with so far were always random variables x and y, which took on a finite number of values. Essentially that. So they were able to, they could take on a finite number of values, and the typical example was x takes on 2 values, 1 and 2, and y takes on 3 values, 1, 2, and 3. But the important thing is that they were finite, and then we allocated to them a probability, and over all the values that they could take on jointly or each one individually, this thing summed to 1. This is called, or what we've looked at previously is called that we dealt with discrete random variables and their associated probability mass function. Probability mass function. So if you want to visualize that, for example, for one random variable, and you consider here a set that you all know now, the real numbers, we actually didn't look at the fact that x could take on real number, could take on all values in the real number set. But what we looked at is that x could take on, for example, the value 1, and x could take on the value 2, and not any other value. Yeah? And then we allocated to it a probability. For example, here 1/3, and here 2/3. And this is the typical thing that one uses to introduce computing with probabilities, because then these probabilities sum to 1, and it's everything is quite clear. But it's actually not the case that we need when we want to look at the GLM, because in the GLM one assumes that the outcomes of random variables of interest, so especially our epsilons here, they can take on values in the real numbers. Yeah, so the reason for that is essentially that we want to model data that is not discrete but continuous. Because, for example, EEG measurements or fMRI measurements is not a discrete set of like 1, 2, 3, 4, 5 values, but it's many values over a continuous scale. Yeah. Although, as a side note, of course, in a computer everything is discrete. So in principle, so this whole thing of continuous continuity in math is a little bit old-fashioned, because everything in a computer is quite discrete. But then one can argue that we still conceive reality as continuous. So a mathematical model of reality is better a continuous model. But again, that's like one doesn't really know whether the world is probabilistic or deterministic, but not comprehensible, and one doesn't really know whether the world is continuous or discrete. But a good model seems to be a continuous model. What does that mean for us? That means for us that you have to be able to carry your intuition that we now introduced for discrete random variables over to the case that x and y, for example, are continuous random variables. So I will sometimes, or actually quite often, write that as now x can take on real values, yeah, or for example values in a real dimensional, n-dimensional space. That's by itself not that hard, because that just means that you allow many different values for the random variable. What is a little bit more tricky at first to come around is that then the summation over probabilities for values that the random variable can take on to 1 has to be replaced by integration, and specifically the probability mass functions that we now establish have to be replaced by what is called probability density functions. So the crucial thing here is that there are now so many values that the probability for x taking on a very specific value in the real numbers is really, really small, and essentially is 0, because you have just a probability mass of 1, and you can ask what is the probability that you can always kind of add another number behind the decimal point and ask, so what is the probability that it takes on 1.32? Yeah, okay, that's that. But what is then the probability that it takes on 1.3, 0.1, 0.4, 0.5, 0.1, and so on. So you have really many and infinitely many values already between two numbers, and then you can also extend this towards infinity in the left and to the right, so to the plus and the minus sign. So there are really many numbers that now, and you only have the probability mass of 1. This summation is not sensible anymore. But what is sensible is that you allocate probabilities to intervals or sets of numbers. And this, what I'm actually talking about here in words and trying to appeal to your intuition, that's actually the foundation of measure theoretic probability theory. So instead of basically assigning probabilities to numbers, you assign probabilities to sets of numbers. And that directly leads to the intuition about probability density functions. So first, let me show you a probability density function that you have seen many times. This probability density function looks as follows. So you have a function that maps the real values into the positive real numbers. So it takes a value x and maps it onto fx, and what it evaluates is this thingy here. So, who has seen this equation? No? Is the psychology people, you have never seen this? You have never seen this? But have you seen this? Good. When your psychology teacher plotted this thing here over x and the real numbers, what they actually plotted was this function, which is called, yeah, it's called the Gaussian. Really? And this formula was not shown. Maybe it looked a little bit different. Maybe this x wasn't there, but it was oh, there was, what did I do? There was there was actually, of course you have never seen that because it was wrong. Jesus, so have you seen this? Don't say yes, no, that would be me. So this you haven't seen. This, what I mean by the x, and we will come back to that, is actually, maybe you have seen it with 1 to the power of something like this. Have you seen this? With e to the power of something?
Like e to the power of 1 over 20?
No, 2 sigma square. Okay, so I thought, so we will discuss this, actually this formula in more detail, because we have to also for the multivariate case. I just wanted to check whether you've seen this, but you haven't. But you have seen this bell-shaped curve. Yeah, good. There's a question. Sigma is supposed to be the standard, there is the standard deviation. Sigma squares the variance, but we will talk about this in detail. At this point, I actually just want to check whether you have seen probability density functions, and apparently you have, even if you didn't write them down as functions, but you've seen this bell-shaped curve. Now, what does this bell-shaped curve tell you? And that's actually more the question. I'm telling you now, and that might be the new thing, that this is a probability density function. So what it assigns to values of x, which are now our random variable, is not a probability, but a probability density. Why is this important? Because fairly soon you will be confused if you actually see some proper labeling of the x's here, and then you will see, for example, something like this. And here x, let's say that this is, I don't know, 2, 3, 4. And then often what is confusing is that now this probability density takes on values larger than 1. Because I've just told you that probabilities all sum to 1. So if you then look at these probability density functions, you will think, oh, why can they be larger than 1? That's strange. But it's not strange at all, because it's a probability density function and not a probability mass function. So if it were a probability mass function, where with discrete values 2, 3, and 4, then one, of course, a Gaussian can never be a probability mass function, but we can think of a probability mass function that I'm now denoting with these stems here. So they would always be below 1 and sum to 1, but probability density functions don't have to be, in terms of their values, smaller than 1, because they assign probability densities, not probabilities. Now, that leads to the notion of density. So we have to think about what is a density. And the best intuition from that is actually from physics. So how, in school, how did you compute the density of an object? Who has computed the density of an object in school? Physics. Everyone. So how did you compute the density of an object in school?
Mass over volume.
Mass over volume, exactly. So you called that rho, I assume, and you divided mass by volume. Yeah, maybe. So that's the formula. So I can also write it in. Can write it in words: mass over volume. Now, what I'm trying to do here is to appeal to your intuition from physics and how you dealt with densities to get your head around probability density functions, because what we've done so far with our random variables in our tables is that we allocated probability mass. Yeah? So we were interested in probability mass, and the probability mass was supposed to sum to 1. Now we're talking about probability densities. And the most important thing is, if we ask ourselves, so what is the probability mass? Then, well, it's the density times the volume. So if I just multiply both sides here of this equation by volume, we get mass equals density times volume. Now, if we don't have any volume, so if we look in the real numbers at only a single point and not a volume, so something, for example, like an interval, then of course our mass that we allocate to that is 0. So if our volume is 0 and we multiply it with our density, we get 0 mass. However, if we actually have some volume that is larger than 0, so not only a single point, but for example an interval, so for example between 2.5 and 3, so we are interested in this interval here, then we can compute the associated mass by looking at the density, and the density is shown here on the in this graph. So that's the density over this. Let's take a different color. So this is our volume here, so the interval between 2.5 and 3, and we want to compute the probability mass for this volume. And basically, from what we know from school physics, says that okay, if we have mass, if we have volume and we want to compute mass, we have to multiply it by the density. And the density roughly in this area is somewhere here. So we are so averaged over these different values. So we can multiply essentially this part with the average density here. What this all is supposed to tell you is that if you want to compute the probability mass that is specified in terms of a probability density function, you need to multiply the probability density with the volume that you are interested in. Now, that was a lot of detail. There's a question?
Yeah, on the density, is the P the sample density of probability?
This is very good, yeah, that's a rho. That's for density, but we can actually get rid of that because I just wrote density and mass divided by what was supposed to be the same thing. Now, this explained now why the densities that you will see sometimes will be above 1. What is actually more important than that, whether the densities are sometimes above 1 or not, is the intuition that you read into density functions. And the intuition that you read into density functions, you can relax completely, because if you have this bell-shaped function here, and I'm telling you x is now a random variable, and it has the associated probability density function px, which is shown here. Maybe I should give it a color so that you can see the difference between the axis and the function. Something like that. So that's now the probability density function. Now, if I'm sampling from the random variable x that has this probability density functions, is it more likely that I sample a value here, or is it more likely that I sample a value here? So who is for 1 and who is for 2? For 1, please. And for 2? Jesus, a lot of people didn't raise their hand. Let's do that again. So I'm saying I want to sample a value of x here, where the probability density is high, and I want to sample a value here where the probability density is quite low. So who thinks it's more likely that I sample a value where the probability density is high? That's the majority. And you're completely right, of course. You can, from what I told you before, you can view that a little bit more abstractly, in the sense that you the probability mass actually to sample a value inside a set somewhere here is, of course, if you compute the probability mass based on the volume and the associated density, is of course larger in case of high densities as opposed to low densities if you think of the same volume. That means that if you see a graph like that, where when I'm saying, okay, this is a probability density function, you can basically infer that if you were to sample from this, wherever you see high probability density, you also have high probability of obtaining a value. Yeah. The reason basically behind that is because that's maybe more for the advanced people, is that it's that what we are using here for the real numbers is Lebesgue measure. So that's sometimes called lambda, and Lebesgue measure of an interval a, b, maybe an open interval, is just b minus a. So if you were doing things with respect to Lebesgue measure, then everything in terms of probability density and probability mass is largely equivalent. But that's more for the advanced users of this course. Have you heard about Lebesgue measure? Yeah, good.
Why do you back it open?
Oh, just because. Yeah, I'm just used to talking about the back measure in this case. But we are not talking about that. So if you're not happy with measure theory and the back measure, you can just always look at what we are doing with the real numbers and probability densities. If there are high probability densities, there's a high probability to sample a value somewhere there in that region where there's high probability density. And if you then see a probability density function and its values go above 1, then you can relax because it's not a probability mass, but it's a probability density. Yeah.
I think I missed something basic. What is probability density?
It's
another computer somewhat, but what is it?
Yeah, it's the density of. So if you think there's something called probability mass, then probability mass is something like in physics that you can associate with things that have a volume, so sets of numbers that have a volume. And you can, of course, also associate with the elements, so with the elements of these sets a certain density. Or, I mean, how can one explain that? If you, density is kind of an abstract thing, right? So if you have an object that has a certain volume and a certain mass, you can compute its density. But if you then, you can only ever recover some mass if you also have some volume. So you can think of you have this volume and it has a certain mass, and then you compute its density, and then you take a small volume, and then you can compute how heavy that is. But if you have no volume, then density is just a characteristic of this kind of thing. For example, this crown that Archimedes put into water or whatever. It's just a property. It's something abstract. So it doesn't. It's not mean. It's just a number that you can assign to a certain abstract to a certain thing. Yeah, but as soon as you have a certain volume, based on of knowing some density, you can compute a mass. And we have some probability mass that we want to assign to the entire real number set, and this mass is limited, but we have kind of infinite volume, so we have to deal with the case that we can only talk about densities. Actually, that as far as deep as I can explain that, unless we go really into measure theory, unless you have a better intuition. Yeah, even
well,
more.
It basically just means that the values reflected in the are more likely to follow them in the
Yeah, that's the exactly. So that's yeah. So that's
and it has to be with that shape.
Yeah. That's the other thing, of course, that I try to explain with a lot of words, that if you have high probability density, you have a high chance of sampling values in the area of high probability density, because in these areas you also have high probability mass, and everything that we explained previously was formulated in terms of probability mass. Now you have to make the step, but it's not a big step. We will just now look at these kind of functions, and you have to associate it with these densities, high probabilities of obtaining samples. And if you're more interested in the real mathematical details, then start working on your measure theoretic skills. I realize that time has run out again, so we cannot really start with Gaussians today, although I showed you the Gaussian briefly. So that means that the big topic then for next week are Gaussian distributions, and there are associated probability density functions, but we have, I think, now all the background required to actually be able to talk about multivariate Gaussian distributions, because we have rehearsed what probability is, what probability mass is, joint distributions, marginal conditional, and also the abstract idea of densities. Yeah, good. Then see you either on Thursday or next Monday. And of course today for the CCNB seminar.